landing at the rate Tehran likely hoped for. Reports out of the region suggest Iran's own daily missile output has been dwindling as its coastal supply chains get hit. Some estimates put it at only around a dozen missiles a day at this point. A supply chain under siege doesn't just run out of roads. Events being Uali, it runs out of the things the roads were supposed to be carrying. Meanwhile, Iran's retaliation has been shifting in a way that should concern everyone watching the humanitarian side of this. Missiles into Bahrain, Kuwait, Jordan, and Qatar are one thing. Those are largely military-adjacent targets. But striking a power and desalination plant in Kuwait crosses into something else entirely, because that's infrastructure ordinary people depend on for drinking water. If both sides keep pushing further into civilian-adjacent infrastructure, bridges with pedestrian traffic on one side, desalination plants on the other, this war stops looking like a conflict between militaries and starts looking like a conflict that increasingly finds civilians standing in the blast radius, whichever side of the Gulf they're on. And that brings me to the oil market, because ultimately, this is the piece that touches literally everyone reading this, wherever you live. Brent crude has been trading in the mid-70s as of this week, a level that reflects the fragile, uneasy calm of the last several weeks. But every analyst tracking this situation is saying some version of the same thing, that price does not reflect what happens if this round of strikes fully collapses what's left of the June framework. If the blockade holds and the bridge campaign continues to expand, multiple forecasts put Brent back in triple-digit territory within days. The market isn't pricing in peace, it's pricing in a pause. So here's where I leave you. We've watched this war go through cycle after cycle of escalation and quiet, negotiation and collapse for almost 5 months now. Every time it looks like it's winding down, something reopens. A broken framework, a blockade enforcement, a strike that goes further than the last one. The bridges in Hormozgan province are just the latest chapter, but I don't think they're the last one. What do you think happens next? Does this bridge campaign push Iran back to serious negotiations, or does it just set the stage for the next round of retaliation? Let me know what you think in the comments, and if you want to stay on top of how this develops night by night, this is a story I'll keep following closely. Thanks for watching, and I'll see you in the next one. And here's what should concern everyone watching. Pressure campaigns often look most successful immediately before they become most dangerous. If Tehran believes its options are disappearing, it may decide to use missiles, drones, cyber attacks, or regional proxies before those capabilities are weakened further. Washington may see the same moment as proof that continued pressure is working. That creates a narrow, unstable window where both sides could misread the other's intentions. One decision, one failed interception, or one strike on the wrong target could transform this campaign from controlled escalation into a wider regional war almost overnight, shaking the global economy. Lines, the places where specific molecules swallow specific colors of light on their way to the telescope. Every chemical compound in the universe has its own signature this way, a kind of barcode written in light, and astronomers have spent generations building enormous laboratory catalogs matching each wavelength to a known molecule. An IR spec alone can resolve light into thousands of individual wavelength channels across the near-infrared, fine enough to catch an absorption dip only a few hundredths of a micrometer wide, a level of precision that simply did not exist on any earlier space telescope pointed at these two worlds. Beginning in 2022 and continuing into 2023, Webb turned its NIR spec and MIRI instruments toward Titan, focusing on an unusually clear window in the moon's atmosphere, a narrow band around 5 micrometers where the haze interferes the least, giving astronomers one of the best chances yet to read what's actually sitting on Titan's ground. The team behind this work was led by Bruno Bazar and Emmanuel Lelouch of the Paris Observatory, alongside a large international group of collaborators, spanning institutions from Caltech and JPL to the University of Bristol and NASA's Goddard Space Flight Center. Separately, in May 2023, Webb also turned toward Pluto, capturing a high-resolution infrared spectrum stretching across a wide range of wavelengths, a kind of data too faint and too poorly resolved for any earlier telescope to use effectively. What the team found when they finally combed through the Titan data was a dip in the light that shouldn't have been there, centered precisely at 5.113 micrometers. That signal showed up independently in both the NIR spec and MIRI observations of Titan, and that detail matters enormously because two separate instruments, built by different teams, calibrated differently, catching the exact same feature is powerful evidence that the signal is real rather than some quirk of a single detector. On Titan, the absorption swallowed roughly 6 to 7% of the light at that wavelength. Picture a dimmer switch on one narrow band of a stage light, turned down by about 6%, not dramatic to the naked eye, but instrumentally unmistakable. A clean, sharp dip against an otherwise smooth spectral curve. Then the researchers went back and checked Webb's earlier Pluto data to see whether anything similar appeared there. It did. The same wavelength, 5.11 micrometers, essentially matching Titan's signal, turned up in Pluto's spectrum too, absorbing roughly 4 to 5% of the light. Two worlds separated by nearly 1 billion miles with wildly different temperatures, atmospheres, and geological histories, both quietly absorbing light at the identical, unexplained spot in the infrared spectrum. But the signal wasn't identical in every respect, and that difference made the discovery more interesting rather than less. On Pluto, the absorption feature was roughly 3 times broader than the crisp, narrow dip seen on Titan's trailing hemisphere, a wider, smearier signature rather than a sharp one. Researchers considered simple explanations, like differences in surface grain size, and found they were unlikely to fully account for the discrepancy on their own. Something about the underlying material, its structure, its mixture with other compounds, or the physical conditions surrounding it appears to be genuinely different between the two worlds, even while the core identity of whatever produces the signal seems to be shared. This is not a story about one strange reading on one distant world. It is a story about the same invisible chemical fingerprint, subtly reshaped, appearing on 2 of the least alike bodies in the outer solar system. Here is where the discovery stops being an abstract curiosity. Titan is one of the most intensely studied places in the solar system precisely because its chemistry, nitrogen, methane, sunlight, and organic molecules raining down through a hazy atmosphere closely resembles what scientists believe Earth's own atmosphere looked like billions of years ago, before life ever appeared. NASA's next flagship mission to the outer solar system, a nuclear-powered, car-sized rotorcraft named Dragonfly, is being built specifically to land on Titan and search for what scientists call prebiotic chemistry, the raw organic building blocks that, on early Earth, eventually assembled themselves into the first living cells. If an unidentified organic compound is sitting directly on Titan's surface in quantities large enough to leave a clear, repeatable spectral signature, and if a related version of that same compound is sitting on Pluto as well, that isn't just a curiosity about 2 cold, distant worlds. It becomes a genuine data point in the much larger question of how common or how rare the chemical stepping stones toward life actually are across the solar system. Confirming that this signal was real and not an artifact of instruments, math, or wishful pattern matching turned into its own quiet detective story. The first and most basic worry the team had to rule out was whether the dip was coming from Titan's atmosphere rather than its surface at all. Titan's air is thick with methane and haze, and plenty of genuine molecular absorption happens up in that atmosphere rather than down on the ground. If the 511 micrometer feature were atmospheric, it should behave in a specific, predictable way, growing stronger toward the edge or limb of Titan's visible disk, where sunlight has to travel a longer, more slanted path through the gas to reach the telescope, exactly the way known atmospheric absorption lines behaved in the same dataset. So the researchers directly compared spectra taken from Titan's disk center against spectra taken near its limb. If the signal were atmospheric, the edge reading should show it deeper. Instead, they found the opposite. The absorption actually grew weaker toward the limb. Think about what that means. An atmospheric gas doesn't behave that way. But a surface material, partially veiled by haze, that thickens toward the edge of the disk, absorbing the telescope's view less and less as that path lengthens, behaves exactly this way. The evidence pointed firmly toward the ground, not the sky. Ruling out the atmosphere didn't answer the real question, though. It only sharpened it. Now the team had to find out what, on the actual surface of these worlds, could produce this exact signature. They went candidate by candidate through known laboratory spectra of ices and organic solids plausible on Titan or Pluto's surface, and one by one, the fits fell apart. Solid acetylene, a hydrocarbon known to exist in trace amounts on both worlds, does show absorption in roughly the right neighborhood. But its laboratory spectrum comes bundled with a second, stronger absorption band nearby that simply isn't present in the Webb data, an inconsistency the team couldn't ignore, even while keeping acetylene on the list of not yet eliminated possibilities. Benzene was considered, particularly in a mixed rather than pure crystalline form, since pure crystal spectra rarely survive intact on a weathered, irradiated surface. Plausible, but unconfirmed. A broader family of organic molecules distinguished by a particular carbon-nitrogen bonding structure emerged as one of the stronger candidates the team flagged for future study, alongside irradiated methanol residues and other radiation-processed organic compounds, both briefly considered and ultimately set aside as incomplete fits. Some researchers outside the core team have also pointed to polycyclic aromatic hydrocarbons, large ring-shaped carbon molecules known to form in cold, irradiated environments and already suspected to exist in Titan's haze, as another family worth testing in future laboratory work, though no published spectrum of these compounds cleanly lines up with the 5.11 micrometer feature either. Every candidate, when pressed hard enough against the measured data, had a problem. None of them cleanly explained both the depth of the signal and its exact shape. There was a second, quieter risk running underneath all of this the whole time, the possibility that the entire signal was simply noise, Deep space spectroscopy, at this level of sensitivity, is a constant battle against instrumental artifacts, cosmic ray hits on the detector, and subtle calibration drift. And researchers know that chasing a single narrow dip in a spectrum can turn into chasing a ghost if you're not careful. The fact that two independent instruments, built by different teams and calibrated differently, both caught the same feature at the same wavelength, was the detail that moved this from an interesting anomaly, probably an artifact, to a real physical signal worth publishing. That's the weight sitting behind this discovery. A confirmed, independently detected signal on two different worlds, surviving every instrumental sanity check the team could throw at it, with every known candidate molecule, one after another, still failing to fully account for it. Here is what is happening right now in 2026. The Bizard and Lelouch team's paper has since been accepted for publication in the peer-reviewed journal Astronomy and Astrophysics, meaning the finding has cleared the scrutiny of independent expert reviewers rather than resting solely on a preprint. This detection sits alongside a broader wave of new Pluto and Titan science coming out of Webb's instruments over the past 2 years, including a separate discovery published in Nature Astronomy in 2025, in which the MIRI instrument directly detected, for the first time, the mid-infrared thermal glow of Pluto's atmospheric haze, confirming a prediction other researchers had made back in 2017 about how that haze actively cools Pluto's atmosphere from within. Around the same period, other Webb observations turned up hydrogen peroxide on the surface of Pluto's largest moon, Charon, a compound scientists hadn't expected to find there at all, alongside confirmations of carbon dioxide ice mixed into its surface. Around the same period, other Webb observations turned up hydrogen peroxide on the surface of Pluto's largest moon, Charon, a compound scientists hadn't expected to find there at all, alongside confirmations of carbon dioxide ice mixed into its surface. The same broader observing campaign has also produced detailed light curves tracking how heat radiates off different terrains on both Pluto and Charon as they rotate, letting researchers work out real physical properties, thermal inertia, surface emissivity, and temperature differences between regions covered in methane ice, water ice, and the dark reddish organic material that stains parts of both worlds. It is worth noting that Pluto and Titan are not the only icy worlds where Webb has picked up chemistry nobody predicted. Neptune's large moon Triton, which shares a suspiciously similar density and surface composition with Pluto, and is thought by many scientists to be a captured Kuiper Belt object itself, is next on the list of targets astronomers want to re-examine at this same 5-micrometer window, precisely because of what turned up here. Distant dwarf planets like Eris and Makemake, both far colder and even more poorly studied than Pluto, are also candidates for follow-up observation, since if this signature really does reflect some shared process happening across icy, sunlight-starved surfaces, it should, in theory, be detectable there too. None of this was possible with earlier telescopes. The combination of sensitivity and wavelength coverage required to pull real physical numbers out of light this faint from targets this distant simply didn't exist before Webb reached its orbital vantage point in early 2022. Taken together, the picture emerging from Webb's ongoing observing campaign is of a solar system far more chemically active than the frozen, finished impression many people carried away from the New Horizons flyby a decade earlier. What most headlines miss is that this 5.1 micrometer detection isn't an isolated oddity. It's one more thread in a fast, thickening pattern of unexpected chemistry showing up across worlds astronomers thought they had already mostly figured out. And there is already a specific, scheduled mission that could finally help answer this. NASA's Dragonfly mission, the nuclear-powered rotorcraft designed to fly between dozens of sites across Titan's surface, is scheduled to launch from Kennedy Space Center no earlier than July 2028. After a roughly 6-year cruise through deep space, Dragonfly is set to arrive at Titan in 2034, landing first in the equatorial dune fields known as Shangri-La before eventually hopping its way toward Titan's Selk crater, a site scientists believe may hold traces of past liquid water mixing with organic material. Once there, its onboard mass spectrometer will be capable of directly sampling and identifying the molecules sitting on Titan's actual surface, the closest thing to finally settling what is producing this 5.11 micrometer signature, rather than inferring it from nearly 1 billion miles away through a spectrum alone. Sit with that for a second. A mystery pieced together from data gathered in 2022 and 2023, confirmed and published in 2026, may not get its final answer until a spacecraft physically lands on the surface in question in 2034, 8 years after this very discovery was made public. Now, the honest part, because this is exactly where a lot of coverage of stories like this oversells what's actually known. The research team was explicit in their published conclusions that they could not identify this signature among any published laboratory spectra relevant to either world's known chemistry. That is not a small caveat tucked into the back of the paper. It is the central unresolved fact of the entire finding. The leading candidates on the table right now, whether it's solid acetylene despite its inconsistencies, mixed benzene, more exotic nitrogen-bearing organics, polycyclic aromatic hydrocarbons, or irradiated methanol residues, remain candidates, not conclusions. It's entirely possible the true answer turns out to be a compound that hasn't even been measured in a laboratory yet under the extreme cold and radiation conditions of the outer solar system, since not every plausible ice or organic solid has been characterized under those specific conditions. There's also a second layer of honest uncertainty sitting just beneath the first. Even the width difference between Pluto's and Titan's versions of the signal, treated here as an important clue, is itself only partially understood. The team could rule out a couple of the simplest explanations for that difference, but stopped short of claiming they know the real cause. Two genuinely open questions stacked on top of each other: what the compound is, and why it looks different on each world, with neither one fully answered yet. Step back from the specific wavelength and the specific candidate molecules for a moment, and there's a bigger pattern worth sitting with. For most of the history of planetary science, distant worlds were understood one at a time, in isolation. Pluto's chemistry studied as Pluto's chemistry, Titan's as Titans, each world treated as its own closed puzzle. What Webb's sensitivity is starting to reveal is that some of the fundamental organic chemistry happening at the edges of our solar system may not be local to any one world at all. It may be a shared, more universal process: sunlight, cosmic radiation, and simple molecules like nitrogen and methane cooking slowly over billions of years into similar complex compounds, regardless of whether the world in question has a thick atmosphere and methane lakes, or almost no atmosphere and a surface near absolute zero. That is not what most models built for Pluto and Titan separately were ever designed to predict. It suggests the ingredients for complex organic chemistry, possibly even chemistry relevant to the deep origins of life, might be less about the specific conditions of any one planet or moon, and more about a shared chemical grammar written into the basic materials scattered throughout the outer solar system. Consider how differently this story would have unfolded just 15 years ago. Before Webb, a spectral feature this faint at this specific wavelength, buried in a narrow atmospheric window on two faint, distant targets, would likely never have been detected at all. The instruments simply didn't have the combination of sensitivity and spectral resolution required. Every generation of telescope doesn't just answer old questions faster. It opens entirely new categories of questions the previous generation had no way of even asking. Webb wasn't built with a directive to find an unidentified molecule on Pluto and Titan. It was built to be sensitive enough that, when pointed carefully at the right wavelengths, it couldn't help but stumble into questions nobody had thought to write into its official goals. There is something quietly striking about two worlds this different, speaking in the same unidentified chemical language. Pluto sits in near total darkness, so far from the sun that sunlight there is roughly 1,000 times fainter than on Earth, and yet its surface is not simply an inert block of frozen nitrogen. It is still, after billions of years, cooking something new. Titan, drenched in its own orange haze, with rivers of liquid methane running beneath a sky no human eye has ever directly seen, carries a version of that same signature, subtly reshaped, as if written in a related but not identical dialect. Somewhere in an office at the Paris Observatory, a research team is still staring at a small, unexplained dip in an otherwise smooth spectrum, one that neither the largest chemical databases on Earth nor decades of laboratory spectroscopy have yet been able to name. So here's everything in one breath. Between 2022 and 2023, James Webb captured detailed infrared spectra of both Titan and Pluto. In 2026, researchers led by Bruno Bézard at the Paris Observatory identified an unidentified absorption feature at 511 micrometers on both worlds' surfaces, 6 to 7% deep on Titan, and 4 to 5% deep, but 3 times broader on Pluto. They ruled out an atmospheric origin by comparing disk, center, and limb spectra. They tested known candidate molecules, acetylene, benzene, nitrogen-bearing organics, polycyclic aromatic hydrocarbons, irradiated methanol residues, and none of them fully matched. The paper has since been accepted for peer-reviewed publication, joining a wider wave of unexpected new Pluto system chemistry findings from Webb over the past several years. The best chance at a definitive answer likely won't arrive until NASA's Dragonfly rotorcraft lands on Titan in 2034, following a launch currently scheduled for no earlier than July 2028. Until then, the identity of whatever is sitting on the surface of two of the strangest worlds in our solar system remains genuinely, officially unknown. What makes this story worth remembering isn't just the mystery itself, it's what the mystery represents. Two worlds, separated by nearly 1 billion miles of vacuum, arrived at by entirely different geological paths, are quietly telling scientists the same thing in the same wavelength of light, that there is still a layer of chemistry out at the edge of our solar system that no textbook, no laboratory, and no spacecraft has fully explained yet. Whatever that compound turns out to be, common or exotic, ancient or newly formed, its discovery is a reminder that even after New Horizons, even after Cassini, even after decades of exploration, these worlds have not finished revealing themselves. The light that carries this secret has been traveling toward us for years, and for now, it is still arriving faster than anyone can translate it.